Welcome to Alpha and Beta Decay. This is BYU Winter 2020 of Physics 106. This is Jonathon Sevy. We're just going to cover a little bit of this cool alpha and beta decay stuff, which are types of radioactive decay. So these are the four basic bullet points we're going to cover. We're going to cover this one real fast because hopefully you kind of get that. There's other videos. If you don't quite understand from this video what we're talking about, please feel free to go watch. Then we're going to cover what makes something radioactive, or why is it prone to decay, which is kind of a good question. We're going to hopefully answer that for you. We're going to go over mainly three types of decay. We're going to do alpha, beta, electron capture, and then we'll throw in fission just as a side comment. It's not really the purpose of this video. Then maybe we'll get to some equations and examples for fun, because that's where all of this gets real fun. So first off, internal components of an element. So circled right now in orange, we have protons that are denoted by the little plus symbol, right? P plus. Now P plus is because it has a +1 charge and 1 AMU, so it has mass. Neutrons, or N, the N naught is maybe not useful, right? You can just say N if you want. Has no charge, has 1 AMU. That's basically what's important. So if you had 1 proton plus 1 neutron, you'd have 2 atomic mass units, which is what AMU stands for. Now electrons, they have a charge, but they have no mass. Now when I say no mass, I know you're going to say they have what up, blah, 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 times 10 to the negative 31. We don't care about mass times 10 to the negative 31, because compared to protons and neutrons, it's so negligible. So we say it has no mass for these type of reactions. Now, what makes something prone to radioactive decay? Well, it's when it becomes unstable. Now, this can be unstable just because you have two positive charges that are in a nucleus that we know are really, really close together. And so Coulomb's law states that there's a huge force because the distance between these is so small. So to balance that, we can throw in, we can throw in some non-charged neutrons in between these two to kind of, give them some space to block the charge. Or we can essentially make this guy get rid of his charge, then there's not as much of a repulsion, right? Or, whatever. Those are basically some of those. Or we could just state that when there's a ton of charges in a huge nucleus, we could just break it up. And if we break it up, then there's not as many charges in a small place. So those are kind of our thought process of what makes it unstable and some of the ways that it would go about becoming more stable. So if we look on an actual compiled graph that I got from this really cool geochemistry book by Francis Albarde, it's really, really quite fascinating book if you ever have the time to read that type of stuff. So as you can see, in a given atom, we've plotted, or a given, across the periodic table, that's what each of these dots are representing, our little atoms. We've plotted them by neutron number and proton number. So you imagine like down there at 1 proton is like your helium, and then somewhere up here you have uranium, right? So as they start to get bigger, you notice they become stable, which is indicated by these black squares, by having more neutrons. And in this gray kind of orb that surrounds the black squares, those are ones that even are possible, that can actually exist. And so you imagine that if they were way up here and they had a ton of protons by this orange dot compared to neutrons, you'd imagine they'd want to migrate somewhere down to this black line, however is possible, so they could be stable, because that's what nature wants to do. But then also you imagine if they're way up here, they just have a ton of mass. The mass is just super, super, super huge. So they might split into two things, right? If we just split that in two, one half might come down and be there, and the other half might come down and be there, right? And that would get them to that black line. You also could imagine other ways that these fringe guys that are unhappy in the gray zone would want to migrate in as a function of protons and neutrons, which is just a really phenomenal way of visualizing it. So let's cover just a couple basic types. So first off, we'll in white do alpha decay. He's like a little happy fish. Alpha decay is when you have your nucleus that decides it's really big, and so it ejects a helium particle, which is just 2 neutrons and 2 protons, which is why it has a mass of 4, but an atomic number, or the number of protons is 2, right? But you get your mass by the 2 neutrons. So that's one way. If you're just massive, you could shoot off an alpha particle. We also, we'll do this guy in blue, have beta minus decay. And beta minus decay, this is when it gets weird, and it's one of those things like field lines where you just have to know that you have to think about things so that you can imagine what's going on, although the particle physicists and crazy people might tell us that this isn't exactly the correct exact thing that's happening. But the best way of thinking of it is that a neutron is actually comprised of a proton that's bound to an electron, which I know you're thinking that's crazy. But if you think of it that way, beta decay is when a neutron emits an electron, and what is left over is a proton. And so it actually kind of works to think of a neutron as being a proton that's stuck really, really close with an electron. And because they're so close, their charges balance each other, so they have no charge. That's a good way of thinking of it. Now, if you inverse this, we call it electron capture. It's just the same thing in reverse. So you have a proton, and he gets lonely, so he reaches out into the electron cloud that's surrounding them, probably the s orbital that's getting shoved in by all the other electrons that are repulsing it. And it grabs that electron and then retires as a happy neutral neutron. There's electron capture for you. Basically the inverse thing. But there's one, I don't know what to call it. It's harder. It's more of where you're like, okay, I can get a neutron being an electron and a proton. But then there's beta positive decay. And beta positive decay is a little harder to wrap your head around. But if you have a proton, and that proton wants to get to a neutron, another path it could take is just by deciding it doesn't like this positive charge anymore, right? Because, you know, who wants a positive charge? So it emits a positively charged electron, or a positron. Now, one way you could think of this guy is that it's a massless positive charge. So basically, it shoots off the charge from the proton and becomes a neutron. This one kind of is weird, and you have to be like, wait, but if a neutron is a proton with an electron, then how can a proton be a neutron with a positron? And again, these are ways of visualizing what we see happen. It's not actually the most technical way of describing it. Like, you'd have to get into quirks and all that weird stuff, which again, if you watch the video on electrons, they explain it way, way, way more in depth. The last one that's just fun, extra credit you might say, is fission. And basically, that's where you have this particle, and this part decides to shoot off and be, I don't know, like nitrogen, maybe we shouldn't use an N, because we're already using an oxygen with 8, and this guy decides to shoot off from this big heavy thing and be, I don't know, like arsenic, right? Which is, I forget what arsenic is, maybe it's like 33 or something. And so you basically are just taking a molecule and you're splitting it into 2 different molecules. Fission's extra credit, you don't really need to know that much about it, but it is super fun. So, now if we look at this super famous example, right, of uranium-238, which, let me get out of white and you can see what I'm marking, is this box up here. And uranium-238 falls in the category where on this number of protons to number of neutrons, it's just way up here, and so it wants to lose mass. Now, it could fission. 235 is generally the fissionable isotope of uranium. So this one instead decides to do an alpha decay. And how do we know? I mean, this little chart down here tells us it's alpha decay. But remember, if you look in this corner, the z-axis is protons, or the y-axis is protons and the z-axis is neutrons. And so if you come over by 2, what you're saying is you are losing 2 minus 2 neutrons. And if you go down 2, you're saying you're losing minus 2 protons. And so if you add those up, you move this arrow just over here. Let's see if it'll drag. You see it's basically the same thing, right? You add the essentially vectors together and you get just this diagonal arrow down. So that's what a graphical representation of an alpha decay would look like. So you'd see alpha decay here, 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 and then you see more down here, 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 right? So this process to get from 238 of uranium to lead 206 is a super long little alpha decay chain, but intermediate is beta minus decay. And how do we know it's beta minus decay from this? Well, remember we stated that a neutron shot off an electron and became a proton, so the mass has to stay the same. But the mass goes from being neutron heavy to proton heavy, because this is your proton axis and this is your neutron axis. So you're shifting it from being a neutron to a proton while keeping the same mass. So anytime it steps up this way, it's beta minus decay. Now, this way could be electron capture, beta positive decay. So that becomes more messy, but for this one, it's super nice. So now we'll just say in green, we have beta decay, and then come down here to beta decay, beta decay, beta decay, beta decay. Right, so there's also a fair amount of beta decay in this process. Now, using this on a more mathematical term, when does it decay? Well, it decays as a function of half-life, which the half-life is when 1/2 of the material decays. So, if you were to draw a chart of this, we would say, if this is your concentration of element A, so if you have 100 up here, after 1 half-life, which is just depending on what material it is, it's a probability type function. At 1 half-life, half of the material would be gone, so you'd be down to 50. But then in 2 half-lives, half of the 50 would be gone, so we'd be at 25. And if you extrapolate this out, what you'll notice is that the decay goes down in this logarithmic fashion, which is the purpose of this E, right, the natural variable. It's this logarithmic thing, the lambda, that's also just dependent on the material that determines the time, and then also your concentrations, the amount you started with and the amount you have now. This is how you do it. So if you started off with a ton of lead-206 and you had 2 half-lives, then you would have only 1/4 of the initial material left in your T-naught. And that's kind of how you'd use this equation. Super fun to play around with. Hope this was super helpful to you.